Industries spend enormous resources dealing with stubborn coloration in waste streams, processing systems, and contaminated liquids. While Coca-Cola is obviously not industrial waste, it provides an interesting model for this experiment because its color is intentionally designed to be stable, very stable, up to 100 years, far more stable than many colored systems we encounter in everyday life. The dark caramel color can persist for extremely long periods without significant degradation under normal conditions. So, this raises an interesting question. If a redox system can rapidly dismantle that color, what could similar chemistry do elsewhere? But that's not the only thing we are investigating today. This experiment is also about the order of reactions, because in chemistry, timing can be just as important as the chemicals themselves. Two reactions using the same substances can produce completely different outcomes depending on where and when electron transfer takes place. Does the reaction work best before reaching the Coca-Cola, or does it work best inside the Coca-Cola itself? That is exactly what we are about to find out, and as this experiment progresses, you will see why the answer matters. We'll be using two chemicals with rather unusual relationship: vitamin C, also known as ascorbic acid in the lab, and potassium permanganate. Now, if you've worked with either of these chemicals before, you already know they are very different chemicals. One is a common dietary supplement found in pharmacies around the world. The other is a powerful oxidizing agent recognized instantly by its deep purple color. At first glance, they don't seem like a particularly exciting pair, but chemistry has a habit of turning ordinary looking substances into extraordinary reactions. And today, we are going to see whether that chemistry is powerful enough to visibly change Coca-Cola itself. To begin, I prepared the vitamin C solution: 100 ml of water, a spatula of ascorbic acid, and a quick stir. Within seconds, the crystal disappeared completely, leaving behind a perfectly clear solution. Nothing dramatic, nothing colorful, nothing that suggests that it might be capable of doing anything. At least, not yet. Now, here is something interesting. Vitamin C is often known simply as a nutrient, something associated with fruits, immune systems, and dietary supplements. But chemically speaking, vitamin C is also a reducing agent, meaning it can donate electrons during a reaction. And that property is going to become very important later in this discussion. For now, I set the solution aside because vitamin C wasn't going to do this alone. It needed a partner, or perhaps a rival: potassium permanganate, a chemical famous among chemists for one very obvious reason: its color. Just a small amount entered the water, and almost immediately, the entire beaker changes into deep purple color, almost black from certain angles. A color so intense that tiny quantities can dramatically change the appearance of very large amounts of water. After stirring until everything dissolved completely, the second half of the experiment was ready. But before introducing either solution to the Coca-Cola, there is something important you need to see. Because these two chemicals already have a history together, a very unusual one. If potassium permanganate and vitamin C are mixed together as powders and enough friction is applied, the reaction can become surprisingly energetic. So I placed both chemicals into a mortar and started grinding. At first, nothing happened, just powder. Then more grinding, more pressure, more friction, and suddenly heat, a lot of heat, enough to trigger visible combustion, which is honestly remarkable when you consider what we are looking at. One substance sold as a vitamin, the other are often used for laboratory demonstrations and water treatments. Yet, together, under the right conditions, they can release enough energy to produce flames. And saying that immediately made me wonder something. If these two chemicals can react this aggressively with each other, what happens when that chemistry is directed towards one of the darkest food color systems in the world? There was only one way to find out. With both solutions prepared, it was finally time to confront the Coca-Cola. I measured out approximately 150 ml of Coca-Cola into a beaker, the dark brown liquid that started this entire experiment. And for the first test, I decided to keep things simple. Vitamin C first, then observation. The solution mixed easily. I stirred thoroughly Washed carefully and waited, and nothing happened. No bubbling, no visible reaction, no dramatic color change, nothing at all. At least, nothing that could be seen with the naked eyes. And honestly, that was a little surprising, because vitamin C is known for its reducing properties. If it was going to attack the coloring compounds, you might expect some visible signs. So, I set that beaker aside and moved on to the second test. This time, potassium permanganate, the deep purple oxidizer, the chemical responsible for the flames we saw earlier. Surely, this one will do something, right? So I poured the potassium permanganate solution into the Coca-Cola. Again, I stirred, watched, and waited. And once again, almost nothing happened. No dramatic transformation, no sudden disappearance of color, no obvious sign that the Coca-Cola cared about my plants. Now, this was getting interesting because individually, neither chemical seemed capable of producing the effect I was looking for. Vitamin C failed, potassium permanganate failed, which raised an important question. What if the real reaction wasn't between the chemicals and Coca-Cola? What if the real reaction was between the chemicals themselves, inside the Coca-Cola? So I took the two mixtures and combined them. The moment they met, things started changing. Not explosively, but visibly. Very visibly. Look closely, the dark color was beginning to lose its grip. The liquid was becoming brighter, clearer, more transparent, and for the first time in the experiment, the Coca-Cola appeared to be losing the battle. This is where comparison becomes important because our eyes adapt quickly. A color change can seem small until you place the samples side by side. When I did exactly that, the difference became obvious. The original Coke remained dark, dense, and opaque, but the reacted sample, it has shifted towards transparent brown appearance, still colored, but noticeably lighter. Something inside a drink had clearly changed, and that was exciting because it confirmed the central idea behind the experiment. The chemistry was working. The color could be altered. The question now was, could it be pushed even further, or had we already reached the limits? But I wasn't satisfied yet, because while the Coca-Cola was lighter, it was still very much Coca-Cola, still brown, still carrying a significant amount of color. And that made me wonder something. Was the reaction running out of strength, or was it simply not using enough chemicals? There was only one way to find out, so I increased its concentration. I returned the remaining potassium permanganate solution and added more water, then added another spatula of potassium permanganate. The purple color immediately deepened, suggesting a larger amount of oxidizing agent was now present, at least in theory. Then I prepared a fresh vitamin C solution, and everything reset for the next phase. This time, I measured out approximately 200 liters of Coca-Cola, a larger sample, and hopefully a larger result. But before adding anything to drink, I decided to try something different. Instead of allowing the reaction to occur inside the Coca-Cola, I first mixed the vitamin C and potassium permanganate together. Almost immediately, the familiar purple color began disappearing, and that's actually a very important observation because potassium permanganate is famous for its intense color. When that color vanishes, it usually means the chemistry is changing dramatically. Electrons are moving, compounds are transforming. The reaction is actively consuming the purple permanganate species, and within moments, the solution became clear. I poured the reacted mixture into the fresh Coca-Cola, stirred thoroughly, and waited, expecting an even better result than before. After all, more chemicals, more reaction, better outcome, right? Wrong. Because what happened next was completely unexpected. The liquid remained darker than the sample from the first phase, significantly darker. In fact, although it was slightly lighter than the original Coca-Cola, it was nowhere near as successful as the previous attempt. And that didn't make much sense, at least not immediately. We had increased the amount of reactants, we had increased the concentration, yet somehow the result had become worse, not even better. Maybe the amount of chemical wasn't the problem. Maybe the timing was, because by allowing vitamin C and potassium permanganate to react with each other first, perhaps they had already spent much of their chemical energy before ever reaching the Coca-Cola. It was time for one last test. At this point, the experiment had produced 3 important observations. Vitamin C alone wasn't enough. Potassium permanganate alone wasn't enough. And allowing them to fully react before reaching the Coca-Cola wasn't ideal either. So I decided to try one final approach, and honestly, this was the one I had been most curious about from the beginning. But this time, the battlefield would be different. The Coca-Cola would become the reaction vessel, the meeting point, the place where everything happened at once. So I poured the fresh Coca-Cola, then I poured the potassium permanganate solution, then the vitamin C. And the moment both entered the drink, something immediately felt different. The reaction started almost instantly, not with flames, not with explosions, but with something much more interesting: the color. Look closely, very closely, because this is where years of chemistry become visible to the naked eye. The deep brown appearance that defines Coca-Cola was beginning to break down. The darkness was fading, transparency was increasing, and unlike the earlier attempts, the change was happening quickly, very quickly. At this point, I wanted to push the reaction further, so I added another spatula of vitamin C, then continued stirring. And what happened next was exactly what I had been hoping for. The transformation accelerated. The liquid became progressively lighter, then lighter again, and then something remarkable happened. The Coca-Cola was no longer behaving like Coca-Cola. The familiar dark appearance was disappearing, replaced by a transparent golden brown liquid, clear enough to see through, clear enough that if you didn't watch the experiment from the beginning, you might not even believe it started as Coca-Cola. Now, it's important to understand something. This does not mean the Coca-Cola has been converted into water. Far from it. The sugars are still there, many dissolved compounds are still present, and the drink remains chemically complex, because we had finally achieved something none of the previous phases could accomplish, and the results were obvious. Or at least, I thought the experiment was over. It wasn't, because several days later, something unexpected appeared inside the beaker. Something alive.